So with acids and bases are just a classification of a type of substance in chemistry. We've actually talked fairly consecutively about acids. We've used them in the lab during the year. So now we're going to define like why they're called acids, and then the other side, which are opposite, called bases. So this first table that we're going through are more just generic properties of these two things. Then we'll get down into the details of like the calculations and what really makes them that way. Okay? So first off, they're both electrolytes, which we learned last time means they conduct electricity. Okay? Interesting fact is that acids actually taste sour and bases taste bitter. Now that doesn't mean you should taste them, okay? But I would encourage you, next time you eat any sort of sour candy, look at the ingredient list, and I guarantee one of the ingredients will be an acid. Okay? Most commonly it's citric acid, which is the same acid in like lemons and limes and things like that. But there are other acids that are like, that they sometimes put in sour candies as well. Bases are bitter to the taste. We don't eat too many bases, but if you've ever had to eat soap, you're eating a base. So that's like the bitterness of soap. Okay? Now we'll look at some of these indicators and on your homework in particular, but there's a lot of ways to identify if something is an acid or a base, and it typically deals with some sort of color change. So there's this type of paper, and there's lots of types of paper, but one of them is known as litmus paper. For acids, it turns red. For bases, it turns blue. But there's two types of litmus. And once again, your homework will actually dive more into that. A paper that you might be more familiar with, it's called the Universal Indicator, or pH strips. I don't know where mine went. But they're just like, oh, here they are. So like, I think sometimes you use these in like 8th grade sciences and things like that, right? So they're a little orange strip. You dunk them in, and then it comes out a color, and then the tube has the range of what it falls under. And we'll talk more about those ranges today. Okay? So other interesting things is bases are slippery to the touch, hence like soap. Acids react with metals to form hydrogen gas. So if you've ever seen on any sort of like, I don't know, like Mission Impossible or something type movie, and they use acid to like melt the doorknob or the lock, it's a little bit sci-fi, but it's also kind of true, depending on the metal and the acid. Acids will eat away metals pretty rapidly. Like nitric acid will literally eat up a penny. You drop a penny in, the penny's gone. So depending on the metal and depending on the acid, they can be very reactive with each other. Okay? And then here are some common ones that are found in our lives that are acids or bases. Now with acids and bases, an interesting thing about them is a lot of people, or a lot of students sometimes have the assumption that acids are more dangerous than bases. But they actually can both be extremely dangerous depending on their concentrations. They're dangerous in different ways in how they react with you, but you spill acid on your skin and it will burn it quite badly. Right? Sometimes I go home and I have holes in my pants from spilling acid on them. Right, so it eats it away. But bases, on the other hand, can also corrode your skin. It's not a burning sensation as much, but it like will eat away the skin as well. So they're both very dangerous when they're really high. But if they're weaker, then they're not as dangerous to us. This is why, like with acids, like soda has acid in it, carbonic acid, and that's why it's like bad for the enamel on your teeth. Is because it eats it away. Same thing, like if you ever drink lemon water or something, you're supposed to use a straw so you avoid it hitting your teeth, right? Because it, once again, is an acid. Fun fact of the day. There you go. You're going to drink lemon water, use a straw. Okay? Now, we have two definitions when we get down to the molecular level of what makes something an acid and what makes something a base. Okay? The Arrhenius definition says that acids form this hydronium ion. Now, hydronium is this H3O+. So make sure you make that connection. When we use the word hydronium, it refers to H3O+. So something that all acids have in common is they all release this substance, and that's what, in a sense, reacts with you and with the metal. Okay? Now, bases, on the other hand, they release hydroxide. So they have this OH as part of it, right? Which is one of our polyatomics that we've looked at before. Now, the cool thing about this is if you take a hydronium, so you take H3O+, and you mix it with hydroxide, you make water. So literally, if I take this extremely dangerous acid, hydrochloric acid, and this extremely dangerous base, sodium hydroxide, and I pour them together, what am I making?
Water.
Yeah.
So you can drink that now?
Just kidding.
Oh.
You could, theoretically, if you did your math right. But if I didn't neutralize it perfectly, it would be a bad idea. But theoretically, yes, you could.
It'd be a fun lab. Don't mess up.
Your life depends on it. Okay, so we can actually make neutral water when you balance them out perfectly. Now the other thing though is something else often is made in the process as well. So like in this case, this one actually is if you do it right because it is just salt water. But other ones would make other salts which you wouldn't want to obviously ingest. So the other way you can also define it is by this transfer of a proton. Now it's interesting to use the word proton because what we're talking about really is H+. Now we've mentioned this before that since hydrogen only has one electron, if it becomes positively charged and loses that only electron, it is kind of just like a proton. So acids are classified as proton donors and bases are classified as proton acceptors. So when we look at a chemical equation like this one way to identify the acid and the base is to move the proton or see where it's moving. So we look at the left and we look at the right. So on the left, I see I have HCl and OH. On the right, Cl is now by itself, and we have H2O. So what that tells me, so take your pencil here and draw that the H has moved from here to over there. Which means that this substance is our acid, and this substance is our base. Because bases accept and acids donate. Okay? So same thing in the next one. To figure out what is an acid and what is a base is you track where the hydrogen goes. So in this one, we have HBr and KOH. On the other side, we get our H2O and our KBr. So we can see that the H has moved over again. So this one would be our acid. This one would be our base, and we get what is known as our neutralization reaction. So one of the things we'll practice today on the homework is that transfer. Yeah, Bryn.
Wouldn't technically the K also be going to the BRs, having
Good.
just tracking the H though?
Just the H. Yeah, no, that's a great point to bring up. Yeah, because the K kind of went over here, right? But in terms of identifying acid or base, it's all about the proton or the H. So good observation though. So all of these are called neutralization reactions, and they always make a water and a salt. But if you don't neutralize it perfectly, you could still have leftover acid or base in there.
Because it's just 50-50%.
Yeah, you just have to make sure they're equal ratio, right? But the crazy thing about atoms, right, is one drop of difference can be quite a bit of difference. So now, water is a very interesting little molecule as we've learned about throughout the year. The crazy thing about water is water can be an acid or it can be a base. So water is classified as both. It's called amphoteric or amphoprotic.
I've been lied to. I've always been told it was a base.
Oh, really? Now, your drinking water might be more basic or acidic, but pure distilled water can be both. It can be acidic or it can be, well, it can, let me put it this way. It can act as an acid or it can act as a base. It depends on what it's with. Now, let's talk really quick and then we'll show an example with water.
So it's like dead in the center?
Yes. Yep, so when we get to our scale, water's right in the very middle. Okay, so a monoprotic acid is an acid that has one hydrogen. So for example, HCl would be classified as monoprotic because it has one proton. Or another example would be HNO3, still just one proton. But a polyprotic has more than one. So like H2SO4, so sulfuric acid would be polyprotic. And another example would be like phosphoric acid, H3PO4. So poly means multiple protons, multiple hydrogens. Mono means just one. Okay, so as we look at this idea of water, so let's look at this top reaction and just like before, track the hydrogen. So on this side to that side, take your pencil and for a smiley face, draw an arrow. Where's the hydrogen moving? Are hydrogens moving from here to here or here to there? Because it's one or the other. So draw it on your paper. So look at the left of what they turn, or look at the right of what they turn into, and then track the movement. Anyone had a chance to take their own guess? Okay, if you drew an arrow like this, you can have a smiley face. Because notice on the right side, it's NH4+. So it gained one more. So then that would mean in this case, water is acting as an acid. And this substance is our base. Okay? But in this second reaction, track the hydrogen. Where's it moving? So once again, look at the left, look on the right. On the right, I see that NO3 is now by itself. So that means it gave up its hydrogen. So now water in this example is acting as a base, and the other thing is acting as our acid. Now, even though water can act as both, it's not a very good acid and it's not a very good base either. That's why it's right in the middle of our scale. But it can behave in both ways. What questions do you guys have about identifying acids or bases from a reaction? So you're going to have some things like this on your homework where you have to identify. Any questions right now? Okay, we're going to... The strength of a substance is all about its tendency to give those electrons away. Not electrons, sorry, that proton or that hydrogen away. So the more willing it is to give it away, the stronger that acid will be.
So acid, gives, just always gives?
Yep, and if it's really, really strong, then it gives all its H's away. Okay? Now, with our strengths of our acids, because they give all their electrons away, we get back to this idea of electrolytes. Yeah, Kenzie.
Why is there?
Okay, so they all fall in this category of electrolytes because they conduct electricity. Now, the stronger an acid is, the better it will conduct electricity.
Why did the companies say water they're filled with electrolytes?
So that's why it's a battery.
What do you like?
You know, companies when they're trying to sell water, they're filled with electrolytes.
Because our bodies need electrolytes. They're very important to how our bodies function. But it just means it has sodium, potassium, magnesium, things like that. Yep, yeah, that's why a lot of batteries, battery acid is to help with that conductivity side of it. We should even, I'll go grab, we can test and see the difference with my light bulb. But strong acids are going to be strong electrolytes, so they'll be very conductive. So if I go grab my light bulb and stick it in the HCl, it would be much brighter than it would be in the vinegar, because it is an acid, but it's weaker than, of course, the hydrochloric acid, right? Now, the other way to identify strong and weak is by the chemical equation. So strong things, so find these two equations at the bottom of page, whatever. I don't know what page we're on, but under the category of strong, and these two arrows are missing from your notes. Everyone see these two equations? So draw in these two arrows under the strong section. When something is strong, it's a forward arrow because it breaks apart all the way. But under the next category where it says weak acids do not break apart all the way. And so for those two reactions, you need to draw an equilibrium arrow. So an easy way to identify if it's strong or weak is by the arrow. If it's equilibrium, it's weak. If it's a full arrow, it's strong. Because weak ones do not ionize all the way, and they would only be classified as weak electrolytes. Now let's review, because we're going to be talking about them a lot, obviously, in this unit, how we named acids and bases when we first learned it. So hopefully this will, we can dig it out of our chemistry brain in there, okay? But first off, the biggest mistake, if you guys remember, or the hardest thing was sometimes we used hydro with naming acids, and sometimes we didn't. That's really the biggest distinction. So the only time you use hydro is if it's a binary acid. Binary acids, you put hydro in the front, ic at the end, the element name squished in the middle, and then end it with acid. So for HBr, we would name this hydrobromic acid. Hydro in front, element in the middle, ic at the end, followed by acid. So try H2SE for a smiley face. How would I name this binary acid?
Wait, you only put hydro, there's
One element. So this should still have hydro because it's only Se. The number of hydrogens doesn't matter. Okay, everyone have an answer? All right, on the count of 3, shout out your answer. Ready? 1, 2, 3.
Hydroselenic acid.
Very good. You said hydroselenic acid. You can have a smiley face. Questions on binary naming? Hopefully that rings a bell. Now the only other type besides binary is if it's a polyatomic. So if it's on the back of your periodic table, you do not put hydro in the front. Hydro is only used for the elements. Okay? For the ones on the back, we do have special endings. So if it ends in ate, we change it to ic. If it ends in ite, you change it to ous. So if I wanted to write the name for the acid H2CO3, I would find CO3 on my polyatomic chart. Its polyatomic name is carbonate. So as an acid, it would be called carbonic acid. But notice no hydro in front. Okay? All right, same thing. Let's try the next one for a smiley face. So name H2SO3 for me. Give me the name for H2SO3. Okay, ready? On the count of 3, shout out the name of it. Ready? 1, 2, 3. Good. It sounds like some of you remembered it's sulfurous acid. There's kind of some weird mnemonic things, but if you put sulfus, you can still have a smiley face because you got the right ending. So that's how it's officially spelled right here. Okay. What questions do you guys have about naming acids? Okay. All right, the final thing we're going to talk about today is now the calculation side of it. So in calculating with acids and bases, it all comes back to, I think Tyler brought it up, how water's right in the middle. And so water is kind of the comparison that they built this scale off of. So what we have found with water is that water will ionize to a very, very, very small extent and make hydronium and hydroxide. Now it's a teeny, teeny, teeny tiny amount. That's why water is still neutral and not harmful to us. But it does ionize and make these two things. Now the ratio of them are perfectly equal. Now this Kw value isn't something you're going to do calculations with. It's just helping you understand where the pH scale came from. So the pH scale is built off of this fact of water, of its ratio of H3O plus and OH minus, okay? The calculation we're going to do is how to calculate the pH of something. Now, what makes something neutral is when the H3O plus and the OH minus are equal to each other. When those two things are equal, it's classified as neutral. When the H3O plus gets bigger than the OH minus, that's what turns something into an acid. So when you have more hydronium than you do hydroxide, that's what makes something more acidic. And then vice versa, if you have more hydroxide, it would get more basic. So the amount of those species is what determines how acidic or basic something is. So our pH scale ranges, and notice because of 10 to the negative 14, from a range of 0 to 14 at room temperature. So the pH scale helps us know whether something is an acid or a base. If you want to label right here, number 7, where water is, that means it's perfectly neutral. And when I'm talking about water in this case, it's like distilled water, right? Tap water can vary. Now, everything that is less than 7, so label this on your scale. So everything that is less than 7 is an acid. And everything greater than 7 is a base. And the farther down the scale you go, right, the more extreme acid or base it typically is. Now, this equation right here is the one math thing we're going to learn how to do today. And if you happen to not love logs, it's okay. All you have to do is push the button on your calculator. That's it. Okay, so right now, everyone pull out your calculators. I can show you how to use this equation. If you don't have one, come grab one from my box.
Wait, can we use one on our phone?
Well, I want you to practice with just what you would use like on the test. Like if you're going to use one of mine on the test, grab one of mine or use one of yours, just so you know how to use it.
Okay, good.
Okay. Now, once again, you don't need to really understand how logs even work. If you want to have that conversation, I can teach you about logs if you want. You're just going to use it to get the answer. Okay? So, the question says, what is the pH of a 0.01 molar HNO3 solution? Oh, I erased my X. Okay, I'll just write over here. Okay, so pH equals negative log of the hydronium. So this is the equation we wrote down in the box. Okay? All you do to find the answer, this is like the easiest math we've done all year. Okay? All you do is you just type negative log of 0.05. Put that in your calculator.
That's our answer?
That's your answer. 1.3. You're done. If you're using one of my calculators, you have to do it backwards. So you have to hit 0.05 and then hit log and then hit negative. I know. I didn't make the calculators.
And the negative just takes it away.
Yeah.
Puts it on.
Okay, questions on how, did everyone get 1.3 on their calculators?
So we can press log 0.05 and then do that back.
Wait, where did we
The
get
negative doesn't matter that much, but
Oh, no.
just what the problem gave us. Kenzie, did you get it figured out?
Yeah, but I don't know like what you mean by press the negative after because it just stays.
So when you hit, oh, good? Okay, now first your smiley face, label on your paper, based on what I just calculated, is this substance an acid or base? Write it down, don't say it.
How do you know?
That is the question. Look at your pH scale. this substance is,
Wait. Whoa.
you just gotta flip your pH scale. So less than 7 is an acid, greater than 7 is a base.
Why would you flip it? Is that
So that's the way it's built. I was saying you had it backwards in your head. So.
Oh, that's the way it's built.
Okay, let's try one
my
more
gosh.
practice problem.
First think of like
Dang it.
Okay, so let's try this one. So literally everyone, it's the same thing. We just take the concentration they gave us, plug it into a log. It's a bigger number, well I guess it's a really, really small number, but you just plug it straight in. Now you can use like the EE shortcut because we're doing like the times 10 thing again. I recommend it.
I know where the EE is.
And you should get an answer of like 8.6
Oh.
if you did it correct. And that makes it a base. Good work.
Yes, I'm learning.
Questions on doing pH calculation.
Where's the EE? Oh my gosh, I just looked.